Okay, so this is a talk about a package for count data regression, joint work with Achim Seileis. The package is currently still available from RForge only, but we hope to move it to CRAN later this summer. And since we don't have a lot of time, here's a quick overview. I'll say something about the contents of the package quickly, and then I'll say something about some of the fitting functions, but the fitting functions are not the main topic of this talk because they've been around for 10 years or so, just from a different package. And then I'll give you a short example involving data from health economics, where the count is doctor visits, and you'll basically see lots of plots. Okay, so let's start at the beginning. And okay, this is a very incomplete, brief list of potential fields of application where you might encounter count data in alphabetical order. But again, it's very incomplete. I'm in economics department, so what I tend to see is data from economics, from finance, actuarial science, but of course count data are available in many other areas. So what you classically use for regression issues with count data is the Poisson model or the negative binomial model, which have been around in R forever, more or less, but there are cases where neither Poisson nor negative binomial is sufficient, and these cases tend to involve special types of over-dispersion, such as excess zeros. So there are many applications, for example, in health economics, where you have something like 60%, 70%, 80% zeros, which means Poisson or negative binomial is not going to work well. And the typical extensions for this type of situation are hurdle-type models or zero-inflation models. Depending on the area of application, people will more or less exclusively use zero-inflation models. In other areas, they will more or less exclusively use hurdle models, but these are the typical extensions for excess zeros. You can also extend models using a mixture approach, so finite mixtures of counts, that's also an option. And you can also extend by modeling all the parameters of a distribution, which for a negative binomial would mean you model the shape parameter of the distribution. So this is something along the lines of the Gamels package that many of you will know. And okay, so of course in R, there is stuff available beyond the Poisson and the negative binomial model, but as always, the challenge is to find stuff because it's scattered across a wide array of packages. What we offer here is some amount of unification. We've collected these zero-altered models, as I call them here. Zero-altered is not an official term. You sometimes also hear zero-modified. I just want to have a term that says hurdle as well as zero-inflation. But zero-altered is not something that's well established. It's used in some areas, but not in all. Okay, and we also offer some diagnostics, which means visualization of fitted models and the like. So here's a quick overview of the package. So the fitting functions here, the first two are not what I'm going to talk about because they've been around for more than 10 years, just in a different package, the PSCL package that some of you may know. We've moved these to the new package because the new package is under our own control, whereas the PSCL package comes from a political science department, and there are other things residing in that package as well. Also, there are a few extensions available in the new functions. Extensions mean that the functions now also handle binomial responses and not just Poisson or negative binomial responses. There's also a new fitting function for zero-truncated models. So zero-truncated means no zeros. In some fields, in the Poisson case, this is called a positive Poisson distribution. But okay, here's the function is called zero-trunc, and it does that kind of thing if you need regression for positive counts. What I will mainly show in this talk is the functions for model visualization, mainly routograms. Routograms, that's an old idea going back to John Tukey in the univariate case, and we offer an extension for regression models, and functions are such that they can handle a variety of fitting functions, as you see here. So the main count data regression models have a routogram method available, and even some fitting functions that are not residing in our own package. It's just that we cannot guarantee that this is going to work 5 years from now because we don't have, these other packages are not on our control. There are also some alternatives which I'll briefly show in some areas. These PIT histograms may be more familiar, where the PIT stands for probability integral transform, so you compare things against a uniform distribution on the unit interval. And we also offer a new implementation of randomized quantile residuals. There were earlier implementations, but these were not generic. So, and we also offer some extra flavors. And there are also a few data sets here from a variety of fields. We might add further data sets depending on what we can get hold of, but currently these are the new ones here. And what may be useful from a programming perspective is that we offer the modified count distributions in the sense of the relevant D, P, Q, and R functions for zero truncated and zero inflated and so on distributions, and also score functions, which means you have analytical gradients available. There are also a few extensions or enhancements of things that are residing in other packages. So for example, there is a negative binomial thing available that works with the FlexMix package for finite mixtures, and there are also a few things available that work with the mboost package for boosting, but this is something I'm not going to show here. Okay, very briefly, the fitting functions here are related to these two models, so these are the main ideas for handling zero inflated data. So you have a zero inflation model, which means it's a two-component finite mixture, and one of the components is a degenerate component, it's a point mass. And the hurdle model does things differently. It has basically a binary switch between zeros and positives, and then for the actual counts, it uses a zero truncated count distribution. That's where these zero modified distributions come in. As I said, in some areas, you will exclusively see the zero inflation way, but we tend to think the hurdle models are often more useful, easier to handle. They have computational advantages, for example, because the likelihood separates. And just to briefly sketch what this does, you can think of a geometric hurdle model where the response is geometrically distributed as basically a function that has two parts. The first is a logit component for the binary switch, and then you have a zero truncated geometric. And these can be maximized separately. The likelihoods can be maximized separately. So this is why the hurdle version is sometimes more attractive. And well, the people in the back row may not be able to see this, but I've put a stylized version on the bottom end of the slide that indicates how this can be done in R. So you can use a hurdle function, you can use GLM plus the zero truncated version if you like. Okay, but these functions otherwise will be used in the background, so we will not see them again in this talk. So the data set I'm going to use is, as I said, from health economics. So the response is doctor visits. So you survey people and ask them how often did you see a doctor during the last 5 months or so. So that's a data set from a package on applied econometrics that's been around for almost 10 years. And the response is called visits, and the covariates are, among other things, some ordinal information on the respondent's health. There's also information on insurance coverage and the like, and some other variables. And I'm just using a subsample here because otherwise some of the plots would be very large, but this is not really important to know at this stage. So that's the response here, and as you immediately see, a Poisson distribution is not going to do well with this. You have a large number of zero counts, and you also have some fairly large counts, so Poisson is not going to fit this very well. So models that I try out and visualize here are the following. You will not see all of them, but or at least not for all applications. So there's a Poisson, there's a negative binomial, there's a hurdle version of the negative binomial, a zero inflation version, there's a finite mixture, and there's an extension along the lines of the Gammel's package that models the shape parameter of the negative binomial as well. So for visualization of the thing, you can use these routograms, which basically aggregate the predicted distribution for the individual observations. And what this plot indicates is that the Poisson is an embarrassment for these data because it underfits the tails and overfits the center. And on the right-hand side, you see that the negative binomial does a reasonable job, because the idea of the routogram is that you have this horizontal reference line that you want to hit, and the negative binomial is far, far better than the Poisson according to this plot. Right, you can also have a ggplot2 version if you must, but otherwise you will see the classical versions in the rest of this talk, but that's available if you like it. And the other things here are these pit histograms that I mentioned. So in some quarters this is more popular, so you compare against a uniform distribution on the unit interval. And again, you see on the left panel that the Poisson is a complete embarrassment, whereas on the right-hand side the negative binomial does a reasonable job. So same result as with the routograms, just a different display. So this here indicates that, well, you can also do that with finite mixtures. So the upper left thing is something that we've seen before. That's a classical negative binomial, same plot. And the thing in the upper right is a two-component finite mixture of negative binomials, which doesn't look very different here. I just want to demonstrate that there's infrastructure available, software available, but it's a little bit better. And the more interesting detail is, of course, what's going on in the lower panel. And these are the two components, the two components in the finite mixture, and as you see, they are quite different in terms of shape. So you have a unimodal distribution as the first component and a zero-modal distribution as the second component, which you could interpret as a healthy and less healthy subpopulation, respectively. So anyway, the point here is just to illustrate that these methods also handle fancier fitting functions. Also to indicate that we can handle stuff outside the package. The thing on the right-hand side is something that uses a fitting function from the Gamels package, a negative binomial, as I indicated, with an extra shape parameter that is also modeled in terms of covariates. So, and actually it turns out that the thing on the right-hand side is a little bit better, but not much better than the classical negative binomial. But again, the point is that there's a different fitting function in the background. Okay, a very brief look at other criteria, numerical criteria, information criteria. And here the outcome would be that the heterogeneous negative binomial is, by a small margin, better than some of the others. The hurdle also does well. If you like the BIC, you would even settle for the classical negative binomial. But that's not the main point here. Very briefly, we also have these randomized quantile residuals available that I mentioned. So this is an idea from the 1990s, has been implemented before in R. We just have a generic version now, and we have several flavors of these guys available. This is not the best fitting model, so don't worry about the fit. So the thing in the upper left corner doesn't somehow display a lot of randomness. It's just a single random sample, and you cannot tell that has built-in randomness. The thing in the upper right panel summarizes somehow what's going on in the background, and the two plots in the lower panel give you an idea of the built-in randomness for the randomized quantile residuals. And the thing in the lower right panel will, yeah, I don't know. My students don't like these plots a lot because they want to call their eye doctor when they see that. You have alpha shading and something blurry at the lower end, and I don't particularly like them myself, but they're currently available. So anyway, thank you. Some things that we might build in later. So we are currently discussing whether to extend the predict methods. So there's a current trend in regression modeling towards distributional regression, meaning viewing the modeling process as modeling the entire conditional distribution and not just the mean, as we traditionally do. And this brings up the question, should we offer predict types of the sort density, probability, quantile, and the like? And this is something we will hopefully solve over summer. And we would also like to offer some diagnostic tests for these zero inflation, hurdle issues, and the like. And again, we hope that the thing will be available from CRM later this summer. Here are a few references. Thank you very much.